Hello, good evening. My name is Kate Sanders, and I'm with the OSU Alumni Association. Welcome to Travel Talks. We have a lot of new folks online tonight. We are so glad that you have joined us. The Travel Talks program invites experts from across the university to learn about the places we travel with the OSU Alumni Group Travel Program. Our program offers about 40 tours a year to trips all over the world for OSU alumni and, of course, friends as well. Everything from small hiking trips, such as our upcoming Moab tour, to land trips and riverboat tours, cruises on small or medium sized vessels. We have all sorts of options. Tonight, you're going to go on a virtual geology field trip with Professor Emeritus Andrew Miegs. Andrew is set to join this trip, the Moab Arches and Canyonlands Escape in April. And if this piques your interest, please note that deposits are due November 24th. So you don't have too long to make up your mind. But before we begin, I have a couple things that I do want to let you know about. First is our upcoming Travel Talks schedule. On Tuesday, February 3rd, we are going to travel with the OSU Campus Arboretum curator, Dan Blanchard. He's going to give us also a virtual field trip of some of OSU's most iconic and historically and regionally significant plants and trees. Then, if you joined us for our Bordeaux travel talk this past September, you may have heard Professor Elizabeth Tomasino say that she would do a virtual wine tasting. Well, save the date for March 10th for that guided online wine tasting. And of course, we'll tell you which wines to purchase before the travel talk, too. Then on April 7th, our travel talk topic will be on food, culture, and travel with senior instructor and food writer Kristen Griffin. Then on May 12th, we're going to hear from Professor Monique Goodell, who teaches courses on animal behavior, cognition, and animal learning. Our Africa safari tours were the inspiration of this talk. From savannah to the sofa, what wild cats can teach us about our feline companions. You can find these talks and all the recordings of all of our others at fororegonstate.org/travel talks, as well as some really great past ones like Anita Grunder's Iceland talk, her geology talk. So you might want to check that out in the recordings. So speaking of Africa, consider joining us in May for a trip to Botswana, Zambia, and Victoria Falls, including the famous Chobe National Park. It's a 14-day trip that offers memories to last a lifetime. Then we are headed to Japan here shortly, but we are going again in May 2026. And this is a land tour through Japan with extensive sightseeing and experiences. So if Japan has been on your list, this might be one that you'll want to check out. And also in June, we are going to Switzerland and Austria. And it's another 14-day adventure that'll travel through the region with a private Lake Lugano cruise, the famed Glacier Express alpine train ride, visits to UNESCO sites, and so much more. So these are just a sampling of some of our tours, and you can find them all online too. Um, Now, travel is a membership benefit, and if you need to renew your membership or you want to join, now is the time. So save 25% if you join now in between November 30th and use code OSUAA25 to receive the discount. Um, Last but certainly not least, I want to thank our friends at the College of Earth, Oceans, and Atmospheric Sciences for all their partnerships on this talk and so many of the others. They have another great lecture on November 20th, 2025, just coming up. It's the Marston Lecture in Geography. And you can join this talk in person in Corvallis or online. So depending on where you live, you've got options. Simply register for the talk and you'll receive the link if you want to join it online. And we will send all of this information up in a follow-up email. So if you've missed any websites or links, don't worry about it. We'll give it to you afterwards. Now, on to our talk. Tonight, We are honored to have Andrew with us tonight. He's the Professor Emeritus of the College of Earth, Oceans, and Atmospheric Sciences, and he recently retired from OSU after 26 years. As a researcher and educator, he enjoyed teaching an introductory field geology class and has been on first name basis with every geology major since he started the course in 2007. During his career, he focused on earthquakes and mountain building and played a central role in the conceptualization and writing of the grant that funded the Cascadia Region Earthquake Center. Hello, Andrew. Welcome.
Good
All
evening.
right.
Thank you.
Yes. Welcome to the talk.
All right, I'm
Okay.
going to just get myself all set up here. And let's see.
Yeah, and if anyone has questions while he's getting set up or during his talk, please feel free to either type them in the Q&A box or in chat. We'll be monitoring both of them. So, and then we'll have a Q&A right after his presentation. All right, take it away.
All right. Good evening, everybody. Thanks so much for joining us tonight. It's the fun thing about giving a talk like this is it's a learning experience because you have to learn about what you're about to lecture about. And this is going to be my attempt to describe the geologic history and some of the sites that you can see in the greater Moab area, which is part of the Colorado Plateau. This picture is a view from in the Wasatch Mountains looking to the south, and the Wasatch lie on the western edge of the Colorado Plateau. I figured I might as well clear the air about who I am and what I've spent my career doing. I was born and raised in Portland, Oregon, and that's me on family vacation in Washington back in the 60s. I got an undergraduate degree from Macalester College, a master's degree from the University of Alaska in Fairbanks, PhD from the University of Southern California, and then I did what's called a postdoc, which is a research position after one gets a PhD at the California Institute of Technology. And after that postdoc, I came to OSU, and I've been here for the remainder of my career. And all of my research is focused on mountain building in one form or another: earthquakes, structural geology, sediments that record mountain building, landscapes of mountain building, and how they change in time. And that history of research reflects my inability to settle down into any one topic to spend my career working on. Topography is one of my favorite ways to start any talk because topography very faithfully records the processes and the processes and timescales of forces that change, create, and alter the Earth's surface. The Western U.S. is no exception. Like if you define the Western U.S. as everything west of the Mississippi, and you take the Great Plains, you notice that, of course, it's a low-lying, low relief, low elevation part of our continent, and that reflects the history of sinking of the Great Basin or the Great Plains and the accumulation of sediment over hundreds of millions of years. Back home over here in Oregon, we know the Cascade Range as a volcanic arc, and its expression at the surface reflects the volcanic history, which stretches back about 50 million years. The Great Basin is another example of a very distinctive topography that's related to the stretching and thinning of the continent that formed the Basin and Range province and it marks the edge of the region that we're going to visit in the springtime, which is in the Colorado Plateau. The Colorado Plateau is described as this area in Arizona, New Mexico, Colorado, and Utah that is high and isolated from the surrounding regions. Moab is a point that I've got on quite a few slides that we're going to use as a reference frame. But this talk is about the geology and the the things that one can see while looking at the Colorado Plateau. What is the Colorado Plateau? Well, it sits within a series of mountain belts in what's called the North American Cordillera. In the good old days, the geologists would call it the Cordillera, but we've come a long way since that time, and it's more appropriate to call it the Cordillera. The Colorado Plateau lies down over here in the lower part of this map, and the map is here to show us that the Cordillera is a mountain belt formed along throughout the western U.S. in Idaho, Wyoming, Montana, southern British Columbia, and so forth, and it creates most of the mountainous topography. The Colorado Plateau itself lies to the east of the Cordillera and is in a region that was also deforming at roughly the same time as the North American Cordillera, but involved much older rocks than what one sees in the main axis of the North American Cordilleran mountain chain. It's the rocks that are in the mountain belt are the same ages and of similar character to the ones that we see in the Colorado Plateau, and it reflects a history that began as an Atlantic type continental margin. So envision the east coast of the US, in which we have subsidence and accumulation of sediments sometime in the late Paleozoic. So that's about 300 million years or so ago. There was a change in the western US from being a passive to being an active margin, and that margin was characterized by considerable deformation over that period into the early Cenozoic that was created the mountain belt through the processes of shortening and thickening of the upper part of the earth. And then following that event, those events, I should say, there was stretching and thinning that created the Basin Range and marked the western edge of the region we're going to visit. The Colorado Plateau was named because it's a region of high elevation and low relief. In this cross section from west to east, where the axis over here is elevation and the axis on the bottom is distance, the Colorado Plateau is this area that lies at about 1.5 to 2 kilometers mean elevation. It has some relief on it, but you notice that the Earth's surface elevation is substantially higher than in the Basin Range to the west and in the Great Plains to the east. To a first order, the Colorado Plateau is a relatively simple geological structure. This is a cross section through the southern part of the plateau, which intersects the Colorado River where it flows through the Grand Canyon in two places. And it shows a couple of features that have been long recognized since the Colorado Plateau was recognized as a physiographic province. One is that it's not very deformed. These are sedimentary rocks that are Paleozoic and Mesozoic. The Triassic, Jurassic, and Cretaceous are the time intervals of the Mesozoic. And you can see that basically the rocks are warped, but they're not substantially deformed, and they sit on top of an older crystalline basement that is, you can see when you are at the lowest elevations in the plateau along the Colorado River. And so to a first order, the Colorado Plateau is a high topographic, low relief surface that is marked by relatively modest deformation of a stratigraphic section that accumulated from the Paleozoic up through the Cretaceous. The Cretaceous is particularly interesting because the Cretaceous rocks preserved at the top of the Colorado Plateau were largely deposited near sea level, and thus the elevation of the plateau has risen from the Cretaceous, which is, let's say, we'll pick the Cretaceous tertiary boundary at 65 million years ago, has risen from sea level to a mean elevation of a little bit less than 2 kilometers, which is actually a substantial amount of creation and uplift of the Earth's surface. In detail, however, the plateau is highly deformed and is marked by significant structural provinces on all sides. I already mentioned that the Wasatch Range is the western margin of the plateau. It's also the western margin of the Basin and Range extensional province. And that extensional province extends all the way around the southern margin of the plateau and up into the Rio Grande Rift, which extends about halfway up the plateau. On the east and north side of the plateau, we have the older structures of the Cordilleran mountain chain, which include the belts of rocks that extend into Canada, and then the unique basement or older involved rocks that underlie the eastern side of the Colorado Plateau, Wyoming, and southwestern Montana. The plateau itself is marked by this white line, and it's broadly describing this region, which has relatively few structures. You see a few arches here that are marked in red and faults that are marked in yellow, but otherwise it's a relatively little deformed region, except when you're in the northern part, which is where the trip will take place in the spring. In Moab, Utah, and I found it earlier, I need to find it again. Oh yeah, is right about here. So you can see that in the region of Moab, Utah, in contrast to the southern part of the plateau, there's a number of faults and folds which have internally deformed the Colorado Plateau. So what I'm going to do here is walk through the stratigraphic column and relate it to some of the major features that you can see in the greater Moab area, and refer to specific characteristics of the Moab region first, then the Canyonlands region, which lies to the south of Moab, and the Arches area to the north. The notable thing about the geology in the Moab area is that it exposes some of the older rocks in the Colorado Plateau, and importantly includes this big blue unit right here, which is called the Paradox Formation. The Paradox Formation is Pennsylvanian, and the rocks in the greater Moab area are, roughly speaking, in age from the Pennsylvanian up through the Triassic, or somewhere between 320 million and 200 million years or so. But the key point about this slide is this blue unit, which is the Paradox Formation. It's an evaporite deposit, which was formed in a warm, shallow sea in the Pennsylvanian, and that deposit alone accounts for a significant amount of the geology and the expression of the geology in the Moab, Arches, and Canyonlands region. It was formed in a basin created by thrust faulting. So what that tells us at this time, and again, Moab is right here, Arches is up here, and Canyonlands is down over here. In this map, we're looking at, here's the Four Corners region down here. I have to remember to keep us all oriented. Utah, Arizona, New Mexico, Colorado. This blue outline is the distribution of the Paradox Basin. It's the basin into which those evaporite deposits accumulated in the late Pennsylvanian, and that basin was formed adjacent to a broad uplift, the Uncompahgre uplift, which was growing and emerging above the Earth's surface and creating what's seen right along here in this little stippled pattern here, alluvial fans and other non-marine sedimentary rocks which were pouring off the mountain range into the Paradox Basin. The reason the Paradox Basin, I'm belaboring this so much, is because if you look at a cross section of this part of the world, where the west southwest is on the left and the east northeast is on the right, and the cross section is a projection of geology to depth. So here's the Earth's surface is the black line, and as we go down the y-axis, we're going to depth into the Earth, and along this axis, the x-axis, we're in distance. And I've got labeled up here where Arches is. It's in this block of rock. Moab lies in this valley right here, and Canyonlands lies in this block to the south of Moab. The blue unit in here is the Paradox formation, which is a salt deposit. And salt is very low density material. And the minute you deposit it and then start depositing other rocks on top of it, these dark, lighter brown and beige rocks are Pennsylvanian and Permian rocks. That salt starts to flow. And so the region of the greater Moab area is characterized by the creation of a bunch of salt diapirs. This is where salt was flowing upward towards the Earth's surface due to the loading of sediment on top of it. And in the literature, these pipes or these pistons are referred to as salt walls because they controlled strongly the subsequent deposition of material on outside of the walls themselves. So the salt is quite important because it flows and it doesn't take much to get it to move upward to a lower pressure area like at the Earth's surface. Another feature of this cross section that I want to highlight is the Uncompahgre uplift, which is this great dark brown rock, which has moved up along these faults relative to the adjacent Paradox Basin out here to the south. And these light colored materials are the sandstones and conglomerates that were eroded off the Uncompahgre Plateau into the Paradox Basin. So the geology here in the Moab Arches Canyonlands region has two forcings on it that are omnipresent throughout the stratigraphy and the subsequent events that occurred and are revealed by the geology in arches and canyonlands. And that is, first of all, salt deposition, which allows for flow of material upward and due to any change in the amount of material lying on top of it, and that the rocks that are exposed here were deposited in a basin related to deformation of the Colorado Plateau in the late Pennsylvanian that went into the Permian. And how do we know that? Well, here's a kind of a complicated cross section, but it's the kind of cross section that tells us how to understand time from the relationship between sediments and structures. So again, it's a cross section. This is depth on the left-hand side and distance on the right-hand side. This is a salt wall. This is the Paradox Formation over here. And these are the clastic rocks that are associated with uplift of the Uncompahgre Massif. And these lighter greenish units all are part of the lower part of the Triassic Moenkopi Formation, which on the field trip we're going to see copious amounts of. But the point that I want to make here is that there are two important kinds of stratigraphic relations here. One is right here. This is a Triassic rock that is draped across Permian rocks that are tilted. This tilt of that unit is not present in this rock. That tells you that these rocks initially began to tilt prior to the deposition of this Permian rock. So the mobility of the salt wall, the rise of the salt, began at the same time, in effect, that it was being deposited. And that rising continued as the Triassic rocks, the younger rocks, were deposited. And we see that from a different relation. If you just look at how thick these rocks are over here, these are different units in the Moenkopi, which are, it's not as important as the fact that across the salt wall, they're draped and become substantially thicker to the north. So although the Uncompahgre uplift was marked by this accumulation of sandstones and conglomerates, the salt mobility continued into the Triassic and affected those units in the bottom part of the Mesozoic section up until, roughly speaking, this green or maybe the uppermost unit, which have much less deflection and less variability in the thickness of the sediment. So the sediments that you can see out here contain a unique record of the tilting and the mobility of the salt, which began almost immediately after it was deposited. Now, that deformation, the Uncompahgre and related faults all trend to the north I got to think about this, northwest, southeast. Here's the Uncompahgre uplift. And you can see here a bunch of red lines, which are faults, and black lines, which are folds. And each one of those is parallel to the Uncompahgre. So these are structures that were of a similar age or formed at a similar time in the late Paleozoic, but they continued to be active because this map is showing you the differential elevation of a Cretaceous sandstone, where the colors are warm, the sandstone is at a low elevation, and where the colors are cool or brown, they're at a high elevation. And the fact that this sandstone was deposited in a shallow sea and had roughly horizontal orientation initially and is now distributed on both uplifts and in associated basins tells you that the deformation related to the Uncompahgre structural fabric continued to be active well into the Cretaceous. So there's a very long-lived history of structural modification of the northern part of the Colorado Plateau as revealed by the sediments and their distribution in elevation and in time. If we turn to Canyonlands, then we're looking at, which is to the south of Moab, we're looking at a younger part of the section. There is, of course, some overlap in time, but we're looking at Permian through Jurassic sediments, which are this dark blue up to this green section up over here. These are the Triassic units right here. Here's the Moenkopi that we were just talking about a moment ago. And the significant part about the significant characteristic of this part of the stratigraphic section is that it's basically not strongly influenced by being in an ocean, but is in fact characterized by non-marine or deposition on a continent. And if you look here carefully, you see the word aeolian appear repeatedly in here. Aeolian means windblown, and some of the famous red rocks with big paleo dune complexes of the same kind that you might see at the Oregon coast are preserved in the Canyonlands area. And they demonstrate that at this time in the Colorado Plateau, the region was relatively dry and relatively arid. And the aridity is indicated by the dune formation, and the dryness is indicated by the non-marine deposition. This is a place I did not realize this is it's just a happy coincidence, okay? There's no premeditation here whatsoever, but this is Dead Horse Point. Apparently on our tour this spring, we're going to go right here so we can talk about this outcrop when we're standing here. But here's the Colorado River. Here are the Permian up through Triassic, up to the Jurassic sediments through here. The Moenkopi was the one we were just discussing before. And this is my slide of the statement of the obvious. It's Canyonlands because the canyons are river canyons. And thus, there must be some history of erosion that is recorded within the Canyonlands that tells us something about when this river landscape was etched into the Colorado Plateau. So again, here's Moab right here. This is the Colorado River flowing down from Colorado out towards the Grand Canyon down over here. The Colorado River has a number of major tributaries in this part of the world, one of which is the San Juan River, the other of which is the Green River. But I want to draw your attention to this feature of the map, which shows this big rim, which is called the Book Cliffs. And you notice that this is at a higher elevation, brown, than the adjacent green elevations. And these river systems are acting to evacuate or erode all of the material. So the differential relief between this rim, for example, and the Uncompahgre uplift over here is because the Colorado River has cut down and removed all of the material that you see below the higher elevation parts of this landscape. And we can know something about how that occurs by looking at the way that rivers cut down into the bedrock. This is a longitudinal profile of the Colorado River. So again, it's a cross section, but in this case, here's elevation, and we're looking at the profile of the Colorado River as it flows through Lake Powell. This is reconstructed in the pre-Lake Powell from pre-Lake Powell topography up across this region through Canyonlands, Moab, and Arches. So this black line is the modern Colorado River profile. And what you see that is that the Colorado River has a fairly steady gradient in the western portion, and then it has a steep gradient and a shallow gradient again. Now, a river that is in equilibrium has a smooth and concave up profile, and this river has two important inflections in the river profile that are called nick points. One is here, and another one is here. And you notice that this one is associated with the salt flowing to the Earth's surface. So the river here is removing material and promoting salt flow in here, which allows for the river to be deflected across that. And if we look at paleo river profiles, reconstructions of the river's surface, like for example, here's 760,000 year old 100,000-year-old reconstruction of the river profile, you notice that all of the river profiles down to the 100,000-year time scale all reflect that. So this salt is continuously mobilized and affecting the shape of the river. Up here in Moab, we have the same effect, but the river has a slightly more complicated incision history. How do you figure out the incision history of a river? The key observation is by looking at terraces that form as a river cuts down through a landscape. So here's the modern Colorado River down here at the bottom, and here's that rim rock that we were looking at before, a higher elevation part of the topography. And up here on this surface and these other lower flat surfaces are preserved gravel. And that gravel or sand that was transported by the Colorado River. And you know that it's transported by the Colorado River, not only because it's spatially associated with it, but because the material in those sedimentary deposits reflects all of the rocks that are present in the basin upstream from wherever the sampling has occurred. So to figure out the incision history, you have to have one river terraces, which are these features labeled Q, AL. Q stands for quaternary, AL stands for alluvium, and most normally they're numbered from 1 being the youngest at the bottom to whatever number is at the top, and that's a convenient way to do it in case you find older, higher terraces, you still have numbers left. Sometimes in the older literature, these were numbered in the opposite direction, and you had the problem where you had this was terrace 1, and then you discovered something else, and you had to use some new code for characterizing the name of that surface. Okay, I digress, which is standard operating procedure for me. The key point here is that these materials can be dated via a whole variety of age dating methods that rely on geochemistry to find out the age at which a surface is abandoned. And so to a first order in the Moab area, we can say that we've cut down from about a 1.4 million year old terrace at the highest elevation to the modern over the last 1.5 million years. And that down cutting has been on the order of about 240 meters or so. But there's more and interesting things to be observed in this profile. Like, for example, look here, this is about a little less than 100 meters of down cutting in about, let's see, 800 to 1, about 700,000 years. But then between that terrace and this terrace, there's only about 20 meters of down cutting in 400,000 years. So we have a relatively rapid, a relatively slow, and then we have a rapid period of down cutting from 300,000 years to the present time over about 150 meters of elevation. Well, if we do this in a couple different places, the profile I just showed you are these orange dots. And if we look at a place upstream, we can do the same thing. Ask, how did we downcut as a function of time? So in this plot, we have height, and on this axis, we have age. So in the plot that we just looked at, we saw that after about 300,000 years ago, we began to downcut. The rate of downcutting decreased to about 100,000 years and then accelerated again to the present. If we go to the upstream, however, you notice that the elevation of the upstream channel is higher than in the downstream area, which means that this area was eroding slower in the upstream than it was in the downstream area. But if we look at the few data points as we go farther and farther in time towards the present, you see that there's an inference that the rate of incision in the upstream area accelerated at a time where the downstream area was incising at a relatively low rate. And this leads to the idea that there is a wave of erosion passing through the Canyonlands, Moab, and Arches region, where Meander is basically just south of Moab, and Dewey is just not south, is downstream. Dewey is upstream, and the terraces allow us to show that there is a wave of erosion passing up the Colorado River profile, yielding the modern profile here, and telling us that there's spatially variable erosion rate in the downstream versus the upstream area as the Colorado River sweeps upward and removes material by the passage of this wave. Okay. Finally, in Arches, you see the youngest part of the stratigraphic column. So the complete stratigraphic column of the Moab, Canyonlands, Arches area extends from the late Paleozoic up into the Cretaceous, and we see different parts of the stratigraphic column in different places. And in Arches, we're looking at the lowest and oldest units are Triassic, but the vast majority of the rocks are Jurassic in age, with a little bit of Cretaceous at the top. And the most famous unit in here is the Entrada sandstone, which is right in here, because this is one of the units which hosts the greatest number of arches. This stratigraphic column is, again, mostly continental with some marine influence, particularly towards the end of the history. So how do you form the arches? Well, there is a strong structural control to this. When you create a warping or a fold in sedimentary rocks, there is fracturing that goes along with it, and that fracturing is often referred to as jointing. And in the Arches region, jointing results in the creation of a landform called a fin, and that's what we're looking at here. This is in, I think, near the entrance to Arches National Park. Here's a river down low. You can see the sediments are flat lying, but there is this very strong linear fabric that is creating these long ribs. These are the fins that are resulting from the joints, just cracks that the rock hosts when there is the slightest amount of warping. So in order to make an arch, the first thing you have to do is make a fin. This is an example of an arch in a fin. This is in the Entrada sandstone, and you can see that the arch is not controlled by the layering because these are two different members of the Entrada sandstone, and the arch is cutting across both of those units. So the arch is a giant hole. How does that hole form? Why does a hole form in a vertical fin of rock? Well, wind erosion is one substantial factor that causes abrasion of the rock surface. But in order to create something of this scale, you need a structural control. And one thought that is out there is that the same joints that we see at the largest scale that create the fins are also present at smaller scales too. So here's a picture of the wall of this arch showing the joints that are schematically illustrated here crossing between two different rock types. And those joints are preconditioning the rock to fail in these windows that elaborate into the larger arches that we'll see. So it'll be fun to go and look at some of these arches and try to test this idea that the joints themselves are an intimate part of the process by which the holes get created in the rocks and the arches are created. And then they last only so long as this upper arch is strong enough to support the load above. And then at some point, they must collapse. So this is a picture from the field station where I taught many years that Kate referred to, a beautiful sunset one time. It has nothing to do with the talk whatsoever. But what could we do next spring? Well, we can look for sure at this stratigraphic record of tectonics and paleoclimate since the Paleozoic that's so beautifully exposed in the rocks of Arches, Canyonlands, and in Moab. There is a mountain building history that is contained by this Colorado Plateau region that is of interest to how the continent has deformed over its time span. And it also includes some of the older record of building of the North American Cordillera in the late Paleozoic. And then we'll be able to spend lots of time talking about how landscape and its evolution are linked to the tectonics, the paleoclimate, and the drainage basins and the river processes that have created canyonlands, jointed the rocks, and allowed for the Colorado River and the associated drainages to remove material from the top of the Colorado Plateau and transit downstream towards the Grand Canyon and ultimately into the Gulf of California. So thanks for coming to the talk, and it's Q&A time, and I'm more than
Yes.
happy to answer questions.
Well, the first one that is a hot topic in chat is everyone is dying to know, is it Mount Rainier that was behind you in that photo when you were young? Or was it Mount St.
Oh,
Helens?
do we have the ability to have like a quick quiz,
A
like a
poll?
pop-up quiz?
Well, there's definitely some theories, and I love it.
Hopefully,
Um,
we're leaning towards Mount St. Helens.
Yeah, they're saying that he was in Washington, so he's
That's good.
assuming it was Mount St. Helens since
Yep.
Mount Hood is in Oregon. And then so then it's been great. And then when some other people are like, well, I don't think there's any lakes by the other one, so it
That
must be.
I can see the comments are piling up from outside. Yes, that is the old Spirit Lake before it got filled in and raised up. And my parents would rent a cabin from the Harmony Falls Lodge, which was owned by Harry Truman, the guy who got buried by the eruption because he figured he'd lived his whole life there and he might as well just get entombed there as well. The cabins were extremely crude, and it was just outside playland for kids, chasing frogs, going on canoes, swimming in the lake, hiking, whatever you do as a kid.
That's great. Okay, well, so then the actual questions about the talk too is one of them. Jim mentioned that there's been some uranium mining in the Moab area, and he doesn't quite understand how it would accumulate there. Do you know anything about that?
I'm afraid that is right at the limit of what I know. I believe that the uranium deposits are that the uranium is an erosional product that is deposited in lake beds, but I really cannot answer that question in any authoritative way now, but by next April, I'll be hopefully more prepared to answer it.
That's great. Well, Corey was wondering if you know why the plateau in the paradox formation doesn't have any folds.
Well, the main reason that the paradox formation is not folded so much is because it's deformed by flow of the salt. And thus it is very deformed, but it's mainly because salt has been flowing around. And there are only a few faults that actually extend from below the sedimentary sequence that I described into the basement that have been active over the time scale of the deformation. The Colorado Plateau is a real enigma in many ways because it seems to be floating in the middle of the Cordillera,
Hmm.
where it's surrounded by all sides by very, very deformed rocks, but it in and of itself is it's not inert, but it's a lot less affected by all the processes around. And there's I don't know, thousands of papers speculating as to why it's such a strange block floating in the
Huh.
in the midst of this big mountain belt. But that's a fun question to consider.
That's interesting. Richard was wondering the same thing I was wondering. He was asking, what do you think caused the contrasting rates of downcutting of the Colorado River?
The 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 contrasting rates of the of downcutting are most likely due to the effect of the salt being uncovered by erosion of the river because that
Mm,
creates a differential rate of motion that it changes base level. Rivers uh, are always graded to what's called base level. It's the lowest level of elevation. So if you change that elevation, then you change the whole river adjusts to a lower mouth, let's say, like the Colorado River itself is thought to have started to cut across the whole plateau when the basin and range extension arrived on the western edge, and that allowed the river to all of a sudden flow out to Baja California, which created a big change in base level that propagated up through the whole plateau and created the, among other features, the Grand Canyon. So the same thing that created the Grand Canyon, the idea that is a base level change that propagates up through the system, is the prevailing idea.
great. Okay. Brad was wondering, what is the current rate of Nick Point migration near the Canyonlands, and how do you expect it to change in the future?
I would have to look at that, but it's on the order of 100 100 kilometers. Let's see, is that right? Per 100,000 years. So it's relatively fast moving. Uh, I'm not going to be able to figure out what this would be in meters per year, but it is the expectation that I would have is that in the Moab area, the incision rate will be low now, but the highest rate of incision will follow that nick point as it migrates upstream. So, like for example, on the trip when we arrive in Grand Junction, we'll be above that nick point, then we'll drive down across it between there and Moab, and thus that time scale is in the hundreds of thousands of years for 100 kilometers worth of horizontal motion.
For the non-geologists on the call, can you remind us what is a Nick Point?
Ah, I know. I tried. I'm sorry, people. I really
No, it's
tried
great.
not to go there's a lot of vogue. I've always thought that learning geology or any science is basically a foreign language more than it is anything else. So the definition of a nick point is just a place in a river where the gradient changes from one value to some steeper value. So I showed that
Got it.
they're on two different time scales in two different places. The river has this big weird warp in it.
Mhm.
That warp is the nick point. And
The
and
rate
it's
of
an
change.
and it's an unstable feature of a river, and that is the wave that migrates up out
Mm,
of the basin with time.
great. Mike was wondering if you could say a little bit why the maze, if you're familiar with these formations, the maze, the needles, and the island in the sky districts in the Canyonlands have such differences.
I can't.
You stumped him, Mike.
I'd have to look at a map, but you know the difference is that one of the first order difference over the whole region is just where you are in the drainage basin because each part of the Colorado Plateau is affected by the rivers that are draining through it and where they are in that erosional history.
Great. Richard was wondering, what are some of the top research questions that are remaining in the Colorado Plateau? Some of those unanswered questions.
The number one question, and it is hotly debated on in almost an antagonistic way, is how old is the Grand Canyon? And
Mm,
I decided to completely omit that from this talk. But there is excellent data which show that the Grand Canyon, the Colorado River was integrated into the Gulf of California by 6 million years ago and maybe by 11 million years ago. But there are also a different kind of information which suggests that at least the eastern Grand Canyon already existed as a canyon by about 60 million years ago. And this is that's a substantial difference in time. And the two camps are unresolved. They
mm,
basically talk to each other, I think, but they are kind of like two political parties that can't talk to each other in some ways. Uh, so that's the first one. That one's a really fun one, but you have to be pretty versed in a bunch of subtleties and complicated things to really elaborate on it. What is the age of the Grand Canyon? And the other question is basically, why did the Colorado Plateau rise from sea level at the end of the Cretaceous about 60 million years ago to its present elevation? And the reason that's a problem is that there's no mechanism to do it. Most normally, when you raise up a plateau, and the two most famous plateaus are the Tibetan Plateau and the Altiplano of South America. Both are big, flat, high surfaces at 4 kilometers elevation, twice as high as the Colorado Plateau. They formed because the crust got thicker, and it's just like an ice cube. If you have a really thick crust, you have a high elevation, and if you have a really thin crust, you have a low elevation. But the Colorado Plateau doesn't have that history of thickening, and so it's it's essentially not known. There's a bunch of
mm,
hypotheses out there, but why it rose up is not clear whatsoever. And maybe by next spring I'll have consumed more literature, but I don't think the problem is going to be solved.
hmm. Are there any other areas that are similar to the Moab Canyonlands area geology, or is it pretty unique just right where it is?
I think the things that make it unique are, one, that it is in this plateau that's sitting much higher than all of the adjacent areas, first of all. Uh, and two, that it isn't that deformed inside of it, so that the main expression, like when we're all driving around out there, is just river erosion.
Mm,
The structural history that I elaborated on is really a relatively modest part of the history, or just the impression that you have when you look at the landscape. And there are plenty of great river landscapes that are like that, which have escarpments like the Book Cliffs. I described that very briefly. You know, the Badlands of South Dakota, North Dakota, they're an escarpment related to an upstream wave of incision that's migrating to the west from the Mississippi, related to Mississippi River drainage basin.
oh, great. Dee Dee was wondering, why is there volcanic activity on the southern end of the Colorado Plateau? Is it the Vulcan's Throne and the San Francisco Peaks?
Yep, another great question that I completely decided to omit from my talk. So thank you. The when you have thinning and extension of the crust, which is what is happens in the basin and range, you often get volcanism associated with it. We have that all over the place in Oregon, everywhere where if you're east of the Cascades, especially in southeastern Oregon, there's all kinds of volcanic rocks that are related to the formation of that part of the basin range. So volcanism is a standard operating procedure
Mm,
consequence of of this thinning, and the fact that the southern and western margin of the Colorado Plateau are marked by extension and thinning goes right in hand with the volcanism.
Great. Rhonda was wondering, how does the various geology affect the plants and animals of the area?
Again, out of my wheelhouse, Rhonda. Sorry. I'm sure it does. Because of course water availability and ecosystems are all intertwined with each other. The Colorado River, the Green River, the San Juan River are perennial streams, but most of the rest of the landscape have ephemeral streams that only flow during the monsoon season of the Southwest. So I would imagine there's strong interrelationship between them.
Definitely. And just because it's one of those obvious questions, one of the things when you go to Moab and the Canyonlands, you notice just the color of all
Yeah.
the rocks, of the sandstone. Do you want to speak a little bit to that?
That color is one of the strong indications of the arid environment in which they form, because when you have a rock that has iron-rich material in it, as those sediments do, they rust.
Hmm.
And that rusting is the red color that you see, and it's very strongly indicative of aridity or being in a very dry climate.
Yeah, when I was young, we hiked the Grand Canyon and our white socks were red at the end and they never they were
So you
done.
you saw the bottom of the sea. You saw the whole
Yes.
stratigraphic stack. You may not have recognized it, but you certainly felt it.
No, I was 7, so I
Yeah,
did not.
good for you.
Yeah. It was a trip down the Grand Canyon I will never forget. Well, hiking back up, I should say, was the part that I'll never forget.
Yeah.
Um, this is wonderful. There's been so many great questions. We did have one at the beginning of the talk, because you were talking about mountain building, and you were a big part of the Cascadia and the Cascadia subduction zone and the research. So he was asking, we're due for that earthquake, and want to know if you just had some thoughts about the big one.
The big one. Um, yes, you should be prepared because no one's going to help you. That's what emergency managers would say, is that if you that you ought to be able to sustain yourself, because there's always going to be somebody who's more emergent in a greater emergency than you are, and that could even include ambulance drivers, police, hospitals, and so forth. The the vexing, unsatisfying first answer is we don't know what triggers an earthquake, and thus we don't know how to predict when it will happen in the future. What we do know is that the last earthquake occurred about, let's see, well, it occurred in 1700 in January, so that's going to be 326 years ago, this January 26th. And the average recurrence interval for earthquakes, if you take all the ones that we know when they occurred, is around between 500 and 600 years. But the longest time between any earthquakes is about 1,050 years, and the shortest time is about 150 years. So there's a very unclear answer as to what do we do with the knowledge that it's been 300 years since the last one. People are working very, very hard on the problem, and there's lots of good information about what has happened in the past, and that's improving. And our ability to monitor how the Earth is changing as it leads up to the next earthquake is also vastly improving. But we simply do not know how to answer this question in a way that makes people feel less unsettled by the prospect of it. So again, the best thing to do is to prepare yourself for it.
Yep, very true. And there are a lot of great talks that have happened with Oregon State over the years about the Cascadia subduction zone and earthquake preparedness. So of interest, there is a lot of really good information out there from OSU if anybody wanted to dive into it. a little bit more. This is great. And then Addison was wondering, do you have any cool facts or fun tidbits about the area that you didn't have a chance to put into your presentation that you came across or wanted to share?
Ah, cool, fun facts. One fun fact is that Moab has a big fault that runs right down through the middle of it, and it's experienced every kind of motion that you could possibly imagine, and it's still an active structure. So there are faults out there that are continuing to move, but it may be mostly related to the salt motion. So I think that's one fun fact, and the other fun fact is just about the what has been driving the Colorado Plateau upward in time. The removal of material off the top of it will elicit a small amount of uplift from just getting thinner, but it's not sufficient at all to drive the bigger picture.
Oh, great. Well, this is wonderful. This is about all the time that we have. We are now right at 6:30, so right at our cutoff. And I just wanted to thank everyone for joining us this evening for this great talk with Andrew. It was very educational and I loved it. It was wonderful. For anyone interested in the travel program, we of course are online at fororegonstate.org.travel. You can see all the trip options there, including the one that we hope to have Andrew on in Moab here coming up in the spring. Yes, we're on Facebook, as some people still are. Um, and then that's it. So just thank you all so much for joining us tonight. I know you had a lot of previous students on this call, and there's so many people that are just saying hi to you and appreciating your talk.
Nope.
And I'll be sure to get all those messages to you so you can read them as well.
Okay, well,
But
thanks everybody for coming.
yes. All right. Well, have a great night.
All right.
Bye-bye.